Hello guys, this is AP problem number 4, starting off with number 7 here. Part A says two nitrogen atoms combine to form a nitrogen molecule as represented by the following equation. Two N nitrogen molecules, gaseous form, yields one N2 gaseous molecule. Using the table of average bond energies below, determine the enthalpy change delta H for the reaction. And here it lists the average bond energies. And so we go to my work for A, right here, and it's, so we know that it's a 3-bond pairing there, so it's N 3 bonds equals 950 kJs, or kilojoules per mole, which we got from the chart. And since it is forming bonds, it is exothermic. And since it's exothermic, that means that there has to be a release of energy, making this negative, therefore making the enthalpy change negative 950 kilojoules per mole. So there's number 1, or actually, should I say A. And here's part B. The reaction between nitrogen and hydrogen form ammonia is represented below. N2 gaseous plus 3H2 gaseous yields 2 ammonia, sorry, having trouble speaking today, ammonia molecules in the gaseous form. And the change in enthalpy would be negative 92.2 kilojoules. And it has to predict the sign of standard entropy change, which is work. Actually, it's not work, I'm sorry, it's order, which is delta S, for the reaction and justify your answer. So part B over here. So since this side has 3 moles of the gas and this side, or should I say 4, because there's 3 here and 1 there, and this side has 2, this side is less orderly than this side. So that means that delta S is negative because it's becoming more orderly as the reaction goes on. And we go to, that was part B, so we're going to part C now. The values of delta G for the reaction represented in part B is negative at low temperatures but positive at high temperatures. Why is this? So as we come over here, we see that G is negative at low temps and high temps, is negative at low temps and positive at high temperatures because we go to the formula here, which is delta G equals the delta H minus temperature to delta S, which is, this is enthalpy and this is entropy. And so at low temperature, I forgot to put the delta here, I'll fix that now. Delta H at low temperatures is greater than temperature and delta S. This, in turn, makes delta G negative. And at high temperatures, it is the opposite. The delta H is actually less than T delta S, making G positive. And that is why it is negative at low temperatures and positive at high temperatures. As we move on to the last one now, this is part D. When N2 gas and H2 gas are placed in a sealed container at low temperatures, no measurable amount of ammonia is produced. I need to explain this. An easy explanation for this is because since it's a low temperature, the average kinetic energy is low. This makes collisions between the molecules more rare, and the correct orientation is also rare because they're moving at such a slower pace. Also, the low kinetic energy also leads to a lack of energy needed to reach the activation energy. So, even when these collisions happen, and they are rare, the energy that the molecules have are not enough to reach the activation energy, therefore not getting the reaction to happen, lacking the ammonia molecules, but keeping the hydrogen and nitrogen molecules still in the container. That wraps up AP Problem 4. Thank you.